Okay. So, let's continue on. So, just before the break, we took a look at the summary slide here of these three types of effector T cells. And a CD8 T cells, and the two different kinds of CD4 T cells. And we talked about the cytokines and cytotoxins that are produced by these cells here. So now we're going to go into a little bit more detail, and we're going to start with more detail on the cytokines, actually really the cytotoxins that are released by activated CD8 T cells after they have become cytotoxic lymphocytes, killer T cells. Here are the cytokines and the cytotoxins that are produced by these killer T cells. And let's continue on in more detail about that process. My voice was doing just fine for the first hour. I took a little sip of coffee and it went down my windpipe to the bottom of my lungs. And I coughed like and I'm not fully recovered from that lung insult. So anyway now, so going into more details about killer T cells and how they do their dirty work or their good work. This is a picture that shows how here's a virus-infected cell, and it is expressing on its MHC1 molecules peptides derived from the virus that's infecting it. And here's a killer T cell. It has a T cell receptor here, and it's going to, that T cell receptor is going to recognize the viral peptide. It has inside of it lytic granules, LGs. Just to help the zoom in a little here. Okay. 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 Lytic granules. This is the microtubule organizing center here, which microtubule cytoskeleton or radiate syndrome. This is the Golgi apparatus, and so forth. And all these things are sort of randomly distributed here. As the T cell receptor then makes contact with the class 1 foreign peptide MHC thing here, and all these things line up. The nucleus, Golgi apparatus, they're all in a line here, organized. And there'll be a question on the last exam asking you to remember that the intracellular organelles are all lined up as we're administering they actually call it the kiss of death. That this killer T cell is going to administer to its victim infected cell. When everybody's all lined up, then a few of these lytic granules here are going to be released onto, their contents are going to be exocytosed into this very confined area here. This is some nasty stuff, this little red stuff, it's being released. And we want to make sure that it's only killing the immediate cell of interest here, not diffusing around and killing all kinds of cells in the general vicinity. So we get it all lined up, release just a few of the main lytic granules, and kill this one cell. There will be, we have maybe 100 or so, I don't know how many we have, maybe it's just 10. We have a bunch, we have some of these. We're going to meter them out a few at a time on each target cell that we encounter. In the meantime, we've also been in the process of synthesizing more of the killer enzymes and so forth via the Golgi pathway here and so forth, and then making more lytic granules. So we're releasing some for killing, and then we're replacing them as we go along, basically. Okay. And here's a picture here But, okay. So here's a bunch of infected, maybe it's influenza virus, maybe this is your lung epithelium. Here's a killer T cell. It comes upon this cell and is administered a little kiss of death. Moves on to the next cell, kiss of death. Next cell, sort of a few minutes at a time. After it leaves this cell, the deed is done. The cell doesn't know it yet, but it's dead man walking, okay? And then a little while after this cell is, the T cell is administered its work here, this guy goes as and dies. So he's just being kiss of death to each one, and as we follow them, and then 5-10 minute successions, we see them going into programmed cell death. Only 5 minutes contact required. What the killer T cell is, so there are two things. The killer T cell has membrane-bound proteins on its surface that will bind to membrane-bound partners of the target cell, and those membrane-bound partners can initiate death events. But I think most of the killing is being done by soluble proteins that are secreted by the killer T cell. These cytotoxins here, there are two kinds of proteins here. A class of proteins called perforins, another class of proteins called granzymes. The perforins will partition into the phospholipid bilayer, and then they will assemble to form a little tunnel through the membrane of the target cell. They perforate the cell surface, okay? Perforate means puncture a hole, okay? And so the perforins open up a channel for these soluble granzymes to diffuse into the interior of the cell through the perforins. We used to think that the perforins would assemble on the cell surface. We now know that, in fact, these proteins take advantage of the receptor-mediated endocytosis pathway, clathrin-coated pit kind of thing. So you have these coated pits, and they're constantly budding inwards to form clathrin-coated vesicles and so forth. The granzymes and perforins get endocytosed this way, and in the more acidified endocytic vesicle, then the perforins are able to assemble and actually, go into the plasma membrane of the vesicle, and then form a channel there. So it's only once this perforins are brought into the interior of the cell in the form of an endosome that the perforins produce the perforating structure, and then the granzymes can pass through that channel into the cytosol, the cytoplasm of the target cell. And these enzymes, so-called granzymes, they activate the programmed cell death, the apoptosis program. We'll talk a little bit more detail about that. The programmed cell death pathway, I expect you've encountered this in at least some of your courses until now, but if you haven't, there are a set of special proteases which will, we have, inside of every cell has little cyanide capsules of one sort or another inside of it, and these granzymes will break open a big cyanide capsule that will cause cutting up of the DNA, or changing the phospholipid content of the exome. In a very stepwise way, the cell disassembles itself, okay, and breaks up into small, bite-sized pieces that macrophages can engulf. Okay, and each of the little separate sort of pathways is initiated by a particular caspase enzyme, which will cleave the target, and the target will cleave other things, and it will cascade of events will initiate DNA breakdown, or a bunch of different things. Okay. Now there's also a surface protein on the killer T cell called the Fas ligand, and whenever cells become infected with a virus, or Fas is interesting. Fas is another thing. It's a protein that becomes expressed at the cell surface, and if it encounters its ligand, that protein called Fas will initiate a programmed cell death pathway. So the immune system cells, after they've done their work, they start to express the Fas protein, and then other cells that come along with Fas ligand will activate Fas on lymphocytes and they will then kill themselves in a tidy way. Here's a page from the cell, normal cell, showing the little piece up here. Here's the target cell, okay? I'll go a while this second. This is a virus-infected cell, okay? And just for the purpose of illustration here, we're showing it being killed by 2 killer T cells, one on each side, okay? This cell is killing the target by secreting granzymes or perforins, which are going to get into the cell and initiate programmed cell death. This killer T cell is using the membrane-bound Fas ligand molecules to bind to the Fas proteins here, which will initiate a second way of turning on the same apoptotic caspase program. And this just shows the marked up this one, haven't I? So here's our killer T cell up here, and here is the virus-infected target cell. This T cell is secreting perforins here, which are going to be able to form this channel-like protein structure here once we get into an endosome. And here are these proteases with this granzyme B, which is a protease, and will in turn activate the caspase proteases, which mediate programmed cell death. The granzyme and the M6P molecules, the granzymes and the perforins have a certain kind of sugar called mannose-6-phosphate, okay? And all cells express on their surface a so-called M6P receptor. If you took me for molecular eukaryotic cell biology, I was 302, we talked about this pathway before. So we bring this M6P receptor comes into cells via the specialized receptor-mediated endocytosis pathway here. So both granzyme and perforin are going to be brought into the cell using the M6P receptor to come into form an endosome here. Okay? This endosome will slowly acidify. When it gets a little bit more acid than it was, that triggers the assembly of the perforin subunits to form this pretty large pore in the membrane of the endosomes. And now the granzymes here, this is pH 5, I guess, over here. The granzymes will pass through the perforin, and now the granzymes are in the cytoplasm, in the cytosol of the cell. Okay, so granzymes will cleave a particular caspase, a kind of an apex caspase here. And in this picture here, we activate the caspase that's going to lead to, let's say, cleavage of DNA or something like this. So one or another caspase, all of which can be activated by granzymes, will initiate the various subroutines of the caspase programmed cell death pathway. Okay. And here's a cartoon representation of a perforin channel. Here we're seeing sort of membrane preparations. You can see right here in negatively stained electron microscopy a little string of perforin channels here, sort of white one with a black interior. You see like 3 or 4 of them here. interpretation of them. Okay. Now, I'm going to take you very briefly through pages 11.7 through 11.8d. So 11.7, 11.8a, 11.8b, 11.8c. I'm just going to briefly go through. These show some details of apoptosis, the sort of apoptosis pathway. I'm not going to ask you details about the apoptosis pathway on the exam. To my summer questions, I go into more details about that. Tell me, who has had in biochemistry or someplace else a little discussion of programmed cell death, caspase activation things? Raise your hand. At least some of you have. So I won't. Anyway, for those who've had it, I'm going to go through it pretty quickly. For those of you who haven't had it, it's going to be a little bit too fast and too abbreviated to do you much help, but maybe you'll get some sense of it. So here we're talking about how this Fas ligand guy here in orange, who's expressed on the surface of killer T cells, how it's going to bind partner proteins called Fas. And by the way, I told you in the first lecture that always the growth factors, binding growth factor receptors must dimerize. Anything you do to growth factor receptors to cause them to dimerize, you can forget about the growth factor. Just add something that will cause the growth factor receptors to dimerize, like anti-growth factor receptor antibody will cause growth factor receptors to dimerize. And a sudden signal just as if you'd give it a growth factor. So the thing about growth factor receptors is that the growth factor simply induces them to dimerize, and then that initiates the process. Interesting, for death receptors that bind death ligands, the death receptors have got to form trimers. So I guess to me that means you want to be real sure you don't initiate. I mean, you want to make it a step more difficult. Okay. So we have the Fas ligand, which is a trimer, and then individual monomeric Fas proteins, and the trimeric ligand induces the trimerization of the subunit proteins called Fas. Having trimerized Fas, we then recruit adapter proteins and so forth here, and then these we then recruit a sort of an initiator caspase called caspase 8 in yellow here, and then caspase 8 will act on little slave caspases downstream. Like here's an inactive effector caspase, okay, and that will then, so this caspase will cleave this inactive caspase, and that will now become, when cleaved, will become active, and the cleaved effector caspase will then bind to an inhibitory protein on a caspase activated deoxyribonuclease. So this caspase will cleave the ICAD inhibitor into bits, making the DNA is now active to slice and dice the DNA in the target cell. Okay. Now, so there are two ways we could initiate programmed cell death. From the outside, like maybe using Fas ligand and Fas, and also internally, there are genes that can be expressed in the nucleus that will make proteins that act on mitochondria, and these proteins encoded by the nucleus. So if the cell, for example, I said growth factors will initiate a death pathway. Well, that death pathway, if we're getting extracellular matrix signal that says I'm in the right place, we'll block that death pathway. The death pathway that gets turned on is genes that encode proteins that act on the surface, outer surface membrane of the mitochondria and make it and permeabilize it. And then cytochrome C, which we always knew as my old man and reporter Clark Kent, doing electron transport for respiration. He goes into a telephone booth and he emerges as Superman, okay? When cytochrome C is released from the space between cytochrome C is a soluble protein that lives in the space between the outer membrane of the mitochondria and the inner membrane of the mitochondria, okay? These gene-encoded proteins that have names like BAD and VAX and things like that, they open up channels, and that permits the cytochrome C to leave this in the mitochondria and come into the cytosol. And their cytochrome C activates a protein called APAF, and then APAF turns on another initiator caspase called caspase 9. Now, there's been a lot of debate whether you could kill it just by the external pathway, or maybe the external pathway acts always in conjunction with the mitochondrial pathway. It's certainly very clear that the mitochondria play a very big role in that. Now there's a protein, an anti-death protein called BCL2 that lives in the membrane of the mitochondria. And BCL2 prevents guys like BAD and VAX from making pores. So BCL2 is anti-death. It blocks the release of cytochrome C that would have been caused by this death gene producing BAD or VAX. There's a bunch of proteins that will do this kind of thing. It turns out that BCL2 and VAX can form heterodimers. When BCL2 is bound to VAX, VAX can't do anything, can't cause mitochondrial permeabilization. If you have, and usually have a little excess of BCL2 over VAX inside of a happy cell. If the cell's getting kind of tense and uneasy, then the levels of BCL2 will start to go on down, levels of VAX will start to go up, and we start getting an excess of VAX over BCL2, and now we can form VAX-VAX homodimers, and they can go into the mitochondrial membrane, open it up, and release the cytochrome C. There are families. The whole story the whole apoptosis story really got started in many ways. Well, it got off the ground, it got airborne. People were realizing that there was something called programmed cell death. It got a lot. Like Rodney Dangerfield, these guys got no respect, couldn't get grants and so forth. Everybody would say, well, I'm not trying to kill a cell, but why do we need a special army? Death is a lot easier than life. But they were pointing out how tadpoles will resorb their tails. And in embryological development, we all didn't have hands and fingers. We had flippers when we were early embryo, and by programmed cell death, we got rid of the stuff, and the flipper turned into a fin that turned into a hand kind of thing. That's a pathway. Cancer biology, we discovered many cancers express a protein called BCL2. And as you now know, BCL2 prevents programmed cell death, okay? So cancer cells, which are messed up cells, and they're sending, I gotta kill myself, signals all the time, okay? But they survive, and mutants have been selected for the counter that by overproducing BCL2 so they can keep on living as cancer cells and so forth. We discovered that BCL2 is anti-death, and we discovered there's a whole family of BCL2 like genes encoding BCL2 like proteins. And BCL2 and BCL-XL are two of the more common ones. These are pro-life anti-death proteins that prevent the formation of pores in the mitochondria. And then there are corresponding proteins that want to form mitochondrial pores, and they have names like VAX and VAC and TIC and FLIC and BAD and things like that. Okay. It's kind of hard to talk about the pro-life and pro-death proteins without getting into current political. This body has her own stuff. Okay. Here we go. So, cell death signals. Don't get me wrong, don't get me wrong. Okay. Cell death signals are going to cause release of cytochrome C from mitochondria and other things. And then mitochondria, for example, that is going to bind to APAF. APAF is form a complex with caspase 9s. These caspases are proteases. An active caspase will come up upon its target inactive caspase partner. It will cleave it, thereby activating it, and so forth. And more blah, blah, blah. Here we have BAX and BAD, like modules making channels for the cytochrome C to leave the intramembrane space, come out and activate APAF. Here we have BCL2 neutralizing BAX or BAC and preventing those channels, that kind of stuff. Now, all that stuff that I just went through is not on the test. I'm just giving you that detail, just FYI. Okay? But here's something I do want you to know for the test. Not at the level of having to just draw this picture for me, but at the level of simply remembering the extrinsic pathway that leads to programmed cell death and the so-called intrinsic pathway that leads to cell death. The intrinsic pathway gets turned on if the DNA is damaged. We turn on the genes to initiate this pathway. We have high levels of oncogenes or cell damage, all kinds of things. We'll turn on a protein called, for example, P53, and P53 will then turn on genes like BAX or BAC or whatever, and we'll have an excess of BAX over the protective BCL2, okay? And then the BAX and BAC guys will form channels that permit cytochrome C to be released. And then APAF1 will then activate caspase 9, okay? And so caspase 9 is the activator and is the initiator caspase of the intrinsic pathway. So here is caspase 9, and it's an initiator caspase for the intrinsic pathway. And up here we have FAST, ligand, and FAST, and we have caspase, procaspase 9, and procaspase 9 is the initiator caspase for the extrinsic pathway. So initiator caspases are caspase 8 for the extrinsic pathway, and caspase 9 for the intrinsic pathway. And both 8 and 9 feed into caspase 3, which has the charming name of being an executioner caspase. Okay? So we have initiator and executioners. Okay? I don't know that caspase 3 is the only executional caspase, but it's a major executioner caspase. And it will turn on all kinds of pathways here that lead to the actual individual events of programmed cell death. Okay? This you will know with the test, probably simply at the level of a multiple choice or a true false caspase. The initiator caspase for the extrinsic pathway is caspase 3, caspase 8, caspase 9. You're going to have to remember. a time-lapse movie here of killer T cells killing their targets, and some other stuff. Maybe I should tell you this. Of course, don't worry about this for the test. But it's interesting here. One of the ways that the caspases come into play here is as follows. I can't remember if I had this on the test, but it will be a simple question if I do. But it's kind of a cool story. I like to tell it. Boy, good luck trying to read this. Here's the plasma membrane. Remember, we have an inner leaflet and an outer leaflet. All members are double leaflet structures, okay? Some phospholipids are confined to the outer leaflet, facing the outside world. Other phospholipids are confined to the inner leaflet, okay? One of the phospholipids which is confined to the inner leaflet is phosphatidylserine, PS. And in a happy, healthy cell, 99.9% of phosphatidylserine is in the inner leaflet. Now, some of it can get flipped up to the outer leaflet, but then there's an enzyme, so-called flippase, which will see this and immediately grab it and flip it back to where it belongs on the inner leaflet, facing the inside of the cell. One of the caspases cleaves the flippase. Okay. And so now the slow process of phosphatidylserine every once in a while sort of flipping to the outside world, that's not counteracted by the flippase, which brings it back in. So over time, more and more phosphatidylserine is showing up on the outer leaflet. It's got to sort of equilibrate to half on the outer, half on the inner, or something like that. But macrophages have a receptor, a phosphatidylserine receptor on their surface, and so when we have a cell that's got a bunch of phosphatidylserine on its surface, that binds to phagocytosis receptors on the macrophage, and the macrophage just engulfs that whole phosphatidylserine coated whole cell or piece of cell and brings it in and degrades it. Apoptosis, the whole point of apoptosis is to basically, there are two ways a cell can die, bloody and messy and inflammatory, just sort of bursting open. That's not good, that causes inflammation. Or apoptosis, which means it breaks up into small phosphatidylserine coated pieces that can be engulfed by macrophages with a very minimum of inflammatory. Okay. Now, that was killer T cells. Okay. Now, so CD8 T cells. Now we turn our attention to the effector functions of CD4 T cells. And again, we have helper 1 and helper 2. So we'll start by looking at the effector functions of T helper 1 cells. Okay, and this is a picture from a general cell biology textbook. Watson's great cell biology textbook. So this just shows in a general way that there are certain bacteria that can get engulfed by macrophages in the usual way. That's what macrophages do. They see a bacteria, they engulf it and bring it in, and then that vessel will fuse with lysosomes and will just liquefy, digest that bacteria that's been brought in. But as we said in the first hour, some bacteria have evolved mechanisms to escape what would ordinarily be the fate of an engulfed bacteria. Some of them can simply get out of the early endosome and get into the cytosol directly. Some of them that can prevent the fusion of this cell with lysosomes. So here are lysosomes, and they're only going to fuse with this to form a structure called a bag of lysosome, and the digestive enzymes in the lysosomes will then gobble up and digest the surface and all the contents of the bacteria. Some bacteria prevent the fusion of the lysosomes, and so they just live inside this initial compartment here. And some simply survive in the phagolysosome. So this is the strategy of tuberculosis, by the way, here. And this pathway here, Coxiella burnetii and Leishmania, we do this. So, as we said, the first part of this evening's lecture, T helper 1 cells. Here's a macrophage, and it's engulfed some intracellular bacteria that likes to live in there, like tuberculosis or leprosy, and the tuberculosis bacteria here, happy as clams, okay, not being destroyed. Then here comes the T helper 1 effector CD4 T cell, and it's going to secrete a number of things which are going to make life hot for the tuberculosis bacteria. They do it in part by secreting cytokines like interferon gamma, and in part, again, like the killer T cells, by using a plasma membrane protein, in this case called CD40 ligand, which binds to the CD40 receptor, I guess you'd call it here. And either one of these two pathways induces the production of very strong, like I said, probably the most effective thing that happens here is we produce like industrial grade bleach in these compartments here. And that does kill the previously happy and content tuberculosis bacteria. Now, so here is a list of the various things that T helper 1, the various so here's a T helper 1 effector T cell, okay, and it releases interferon gamma and CD4 ligand to make life hot for tuberculosis bacteria. It produces FAST ligand to bind to FAST, which causes the death of the infected macrophage, which would release the bacteria, but then they'll get into cells which have been pre-armed by helper 1s already now. They won't be able to do their little fancy footwork ways when they try to get into the next macrophage. Forewarned is forearmed. They secrete T cell growth factor, which will make the T cells, the T helper, increase the numbers of T helper 1 cells. They secrete interleukins here, IL-3, kinase macrophage colony stimulating factor, induces macrophage differentiation in the bone marrow, so precursors to macrophages develop so we make more macrophages to fight the infection. Lymphotoxin TNF alpha permits macrophages to come into sites of infection, and macrophage chemoattractant protein here. You do not need to, I'm not going to ask you to list all these things of what they do. Also, in your book, I want to emphasize that T helper 1 cells also facilitate the killer T cell response to virus infections. Okay, now a little bit more detail on armed effector T helper 2 cells. So here's a B cell. It's the one B cell out of a million that makes an immunoglobulin M on its surface, they can recognize a foreign protein from some infection that we have here. And so this B cell will get stimulated. The B cell, the antibody itself functions as a growth stimulating, a signal transducing. It's like a growth factor receptor. In effect, the antigen is the growth factor, and the antibody is the growth factor receptor. And we, together with the first partner proteins, Ig alpha, Ig beta, we initiate signal transduction from the antibody involved in the transmembrane IgM itself. But then we bring that antigenic protein into the B cell. We cut it up into bits and pieces. We load it onto a class 2 MHC molecule here. And now here's a T helper 2 cell. And it has a T cell receptor that can recognize that peptide. Okay? And that T helper 2 cell is going to now secrete a bunch of cytokines. Okay? One, of course, is B cell growth factor, IL-4. Okay? But we have other things that come into play here. Some of these, IL-4 itself, IL-5, TGF-beta, it plays roles in class switching. Okay? Different concentrations of them, some balance, maybe some other cytokines that we don't yet know. But the T helper 2 cell is now signaling this T cell, this B cell, not just to become a plasma cell, but to become a plasma cell secreting IgG or IgA or whatever. Okay? And then IL-4 and IL-6 are involved in the process of making this other T cells to go into the T helper 2 pathway here and block the T helper 1 pathway, all that stuff. You do not need to know, I'm not going to ask you what other cytokines are involved in class switching. You're just going to remember IL-4 is made by T helper 2 cells, it's B cell growth factor, okay? And just the general fact that other cytokines influence what kind of class switching is going to go on. Okay. Now, I really want to stop pretty soon. I'm very happy to use my illness as a reason to stop working here on weakness. Here's the deal here. There are certain bacteria, like the influenza causing Haemophilus influenza. Okay, and this bacteria, it makes life hard for your immune system because it covers itself with a very thick, slimy polysaccharide coat. Okay, kind of hard for the macrophage to engulf that, for one thing. Kind of hard to get. It's hard for if we have an antibody, we would like to have antibodies that would recognize the sugars of this polysaccharide coat. A B cell that makes an antibody against this thick polysaccharide coat would be useful. Okay, but for the B cell, but for that, if we have the B cell that makes that anti-Haemophilus sugar antibody, we need to be able to bring the antigen into the B cell, degrade it, and load peptides for it on the class 2 molecules, remember? And you can't, it's just, the B cell is going to bring in endocytosis, not phagocytosis, okay? So it might be that if you didn't have a vaccine against this thing, eventually some of these bacteria would be dying, and then the foreign proteins would be recognized by B cells, antibodies, and could be brought in. But if we want to vaccinate against this bacteria, the strategy that's used is as follows. We take a protein that's very antigenic. It's a bacterial toxin protein, but it's been inactivated. Whenever you use a toxic protein and then enzymatically kill it. We call that now a toxoid protein. A toxin becomes a toxoid. And certain bacterial toxoids are, for evolutionary reasons, we mount a strong response against. So the toxoid is going to become a carrier protein. And we're going to chemically couple to it the hemopholytic enzyme polysaccharide. Okay? And now we're going to immunize children with this. So the vaccine against this influenza bacterium is a polysaccharide toxoid complex. So children, there'll be some B cells in the children who have who recognize the polysaccharide component of this vaccine product. That's what we want. This is a B cell that makes an antibody against the thick mucus coat. So this B cell now the antibody will be brought in endocytose. Okay, the peptide part here will be digested up into bits and pieces, and some of the toxoid peptides will be loaded onto the class 2 molecules of this B cell. Okay. And now the T helper 2 cell will be a T helper 2 cell that recognizes that toxoid peptide, and this T helper 2 cell will then secrete the cytokines that this B cell needs to differentiate into a plasma cell and make memory plasma cells. Okay. So now we have immunized the child. Now we have memory B cells that make an antibody against the sugar. So now that if we get an infection, now with these B cells will come to life and they'll bind. We've got our antibodies, and antibodies will coat the surface of this thick, slimy mucus coat here, which will then make them easier, make them more tasty to macrophages to do, just to develop that whole thing now and fight off the infection. Okay. And we'll conclude here, and we'll knock out for this afternoon with this. With this little summary slide here. And it says the 3 classes of effector T cells are more or less specialized to deal with 3 classes of pathogens. Okay. Viruses are going to be defended against by CD8 killer T cells. That's how we fight virus infections. Okay. Now, that's not to say B cells making antibodies isn't good and helpful for fighting virus infections, but really this is the main way we defeat a virus infection with killer T cells. We now know that, for example, that people who get infected with the HIV virus, they have some flu symptoms, but then they control the virus for years, and they're controlling it with their killer T cells. With any other virus, we would eliminate it. HIV virus is particularly nasty, insidious. We cannot clear it with our killer T cells for interesting reasons. But now then, for regular bacteria infections, we're going to use T helper 2 cells to cause the proliferation and differentiation of B cells to make antibodies to fight most bacterial infections. But then a subclass of bacterial infections, like tuberculosis and leprosy, we have to use T helper 1 cells to fight those infections. Okay, that's it for this afternoon. I have run the Scantron